Hello viewers, in today's lecture we'll be discussing the critical speed of a thin vertical shaft carrying a single disc. Now in this discussion we'll be assuming the shaft to be massless. We are going to mount it vertically so that there is no influence of movements due to gravity, and we assume that the entire mass of this shaft and disc system is concentrated on the disc itself. Now, any practical system will have some manufacturing inaccuracies, and as a consequence, let's assume that the center of gravity of this disk, which is denoted by this letter G here, so it is having some offset given by this E. E stands for error or eccentricity. So G is offset with respect to the shaft center, that is S, and O here is representing the axis of rotation of these bearings. Now, as this disc begins to rotate, there will be some net centrifugal force acting in the rightward direction here, and the magnitude of that centrifugal force in the beginning will be given by mass of the disc m multiplied by this eccentricity E into square of the angular velocity. Now that centrifugal force will tend to bend the shaft in this direction. So I'll show you here. And as the shaft bends, the amount of centrifugal force increases further because of this deflection Y. Now, in this scenario, the centrifugal force is now given by m into y plus e into square of omega. Now, this force is being countered by the stiffness of the shaft. If K represents the stiffness, so we have these two forces now. K times Y is acting in the leftward direction at the moment, and the centrifugal force is acting in the rightward direction. So mathematically, when a state of equilibrium is reached, then we have this equation which emerges, and from here we can segregate this Y, which is the instantaneous deflection under equilibrium conditions of this shaft. So if we divide the numerator and denominator by K and invoke the expression that square root of K by M is nothing but the cyclic natural frequency. So here we get M by K, so that is nothing but reciprocal of the square of cyclic natural frequency. So this equation transforms into this one where the deflection Y of the shaft is given by omega. This is the operating angular velocity divided by the cyclic natural frequency. So it is squared, and this is multiplied by the eccentricity E. The units are of length. It could be millimeters, centimeters, meters, or microns. Whatever units of E we have here, the same units will come for Y, because this is a dimensionless quantity. And in the denominator we have 1 minus omega upon omega n square. So if we represent this frequency ratio by R, so we have this simplified expression. Now next we'll take up some special cases. The first case is that when the system starts from a state of rest, and likewise omega is less than omega n. So the shaft bends because of the centrifugal force. So under the influence we have Y. This is the case we have just discussed. As omega approaches omega n, what happens is this ratio omega upon omega n, it approaches unity now. So we have something close to unity multiplied by E in the numerator, and in the denominator we have something like 1 minus this quantity is also quite close to 1, so the denominator becomes 0 but remains positive because omega is, let's say, less than omega n. So this is a very small positive quantity, so as a consequence Y approaches plus infinity. Now the moment omega exceeds omega n, but practically this will be possible only if some damping is available in the system. So in that case the resonant peak will come down because of damping, and will be able to cross over to the other side. So in the other domain, now when omega is greater than omega n, but again very close to it, so we have this is slightly larger than unity, can take it to be as a limiting case around 1. In the denominator we have a quantity which is very infinitesimally smaller than 0. The end result is the magnitude of Y is now again very large as before, but now the sign of Y becomes negative. So from y tending to plus infinity, all of a sudden it approaches minus infinity. So you can say kind of mathematically the two infinities are sort of joined. So as omega increases further, we have the next instance, and now omega is sufficiently large. So now you can see this is a quantity which is greater than unity. This is a quantity which is negative. So y has sign opposite to e, and now you can visualize the shaft as bending in this fashion. So here e is taken as towards plus x direction, y is along minus x direction. So the sign of y is kind of coming down from minus infinity. Now the fourth special case is when omega becomes much larger than omega n. Now this is the scenario that emerges. What happens is, now omega upon omega n is very large and its square is even larger. So in the denominator we can kind of neglect 1 in comparison to this large quantity. So what we end up with is a large numerator here and a large negative denominator. They are nearly equal. So this term, except for e, approaches minus 1, or on the whole this y approaches minus e. So this is a special case. The shaft bends in such a manner that this y approaches minus e, so that the shaft can now the disc can now rotate about its center of gravity. So the shaft's bending will adjust so that this point G coincides with point O. Now let's look at the expression graphically. This is what happens. So along the abscissa we have the frequency ratio, and along the ordinate we have the deflection y. So in the beginning the deflection is nearly 0. As omega increases, the frequency ratio increases. It approaches 1 here. This is resonant frequency. So all of a sudden the deflection tends to plus infinity, and immediately in this vicinity it starts coming back from minus infinity and gets settled to as this quantity becomes large, it gets settled to y approaching minus e. So I'd like to show this with the help of an Excel worksheet. So here if I reduce mass, let us say I make it 1 kg, this peak shifts, and if I reduce E, my amount of error, I make it minus 0.5. So I make it 0.5, it's like this. If I increase it, you can see this whole behavior changes. But what's important here is that if Y is always settling down to minus E. So if E is 2, Y is settling to minus 2. If I make E, let us say 5, whatever the units be, so Y tends to minus 5 as the frequency of operation increases. So that is the mathematical part of it. We'll just see the practical implications of this equation in the day-to-day life. Like for example, in case of washing machines or mixer grinders, all of these machines, they usually operate in the frequency domain on the right, on beyond the resonant frequency. So they have to cross over the resonant frequency during the operation. So when the washing machine speeds up, it shakes violently, and then the vibrations, they settle down to y approaching minus e. Likewise, the mixer grinder, it again, when it builds up the speed, it tends to shake violently. The operator might have to damp the oscillations a little bit by keeping a hand on the utensil, and once it crosses the resonant peak, the vibrations, they settle down. So this very simple expression, it does have strong day-to-day, strong implications in a day-to-day life. Thanks for watching.